All right, hello. We are here with a sort of bit of bonus content for the cybersecurity course, CS 540. Um, this week we're working on SHA 256, and SHA 256 has something in it called round constants. So let's go ahead and figure out how to do something with those. I'm pretty sure I want to run the C8999 image. And I'm pretty sure I want bin bash in there. If I can find the slash key on my keyboard. Okay, there we go. And for some reason it seems like I crash every time I join that, so that's no problem. We'll come over here and we'll do, what was it, podman, exec, it, last, bin bash. That'll probably work. This one's live. Excellent. Okay, should probably figure out how Podman works at some point, but that seems like a lot of work. So that's funny. Okay, so I want to. Wait, can I still just do exec? Can I start it and then? Okay, that'll do. Okay. I want to clear this. There we go. Okay, so we have here's the idea. Okay, so let's navigate to home. When you're working with SHA 256, you have a variety of constants. There's round constants that are used for each chunk of size 512 bits, 64 bytes. And then there is the initial hash values that sort of seed the initial algorithm that are the same and that are only used once. Those are pretty interesting. I'm going to show what they are. I'm going to show one way to calculate them, and then we're going to have a more interesting way to calculate them. So the first thing I think I need to do here is I need to open Vim. Yeah, sounds right. Let's see. And then, so I'm going to do Vim. What do I want to open? I'm going to call this primes. Vim primes.c. Seems right. And then we will split horizontally. Will I? Nope, that's vertically. How do you do a horizontal split? There you go. And then go back and forth between Control W, W, and then which side do I want the terminal on? Over there? I think so. That looks fine. And then I want to invoke bash in that terminal. Okay, beautiful. Does this thing have Python in it? Let's grab that real quick. Okay, so what's going on with the round constants? We've got, I'm gonna grab these just from, oops. Oh, what have I done? I've done all manner of shenanigans. So let's see, am I in, what mode am I in? Okay, I want to paste in some constants from somewhere else. There we go. And then going to paste in the other ones. I don't really know how copy pasting things into the terminal works. I usually like curl and stuff, so it's fine. So over here on the left-hand side of my screen, I have the initial hash values and the round constants. My understanding is these are, mine insert mode, yes. These are the fractional components of the square roots of the first n equals 8 primes. Okay, And I'm gonna get rid of that, and that. Okay. The round constants are. Let's see, what are they? Oh no, that's not what I meant to do at all. Edit anyways. Oh, it's gone. Do I want a horizontal split? How did I split my screen? Let's see. That's not what I wanted to do at all. I wanted to split right. There we go. Okay. Over here we want to be in terminal. And do I have Python 3? Let's see. Bin bash Python 3. Excellent. Okay. So we have the round constants, and we have the initial hash values. Okay. And I need to calculate these somehow. And let's see, we were saying, I'm not going to be so fancy with my formatting this time. Fractional component, square root, first n primes. And then the round constants are the fractional component, cube root, first n equals 64, right? Yeah, primes. Okay. We'll write that. Let's just show how these are calculated real quick. So, it just so happens that this is quite easy to do in Python, which is kind of odd, right? And the reason for that is Python has a sort of bunch of these built-in functions that turn different numbers into each other. So we'll use those just to demonstrate what's going on mathematically. So what do I have? So the first prime number that I'm aware of is 2. The square root of 2 is 2 to the 0.5 power, which is 1.414, and some other stuff after the 414, right? And so the fractional component of that is 0.414. Or, you know, we do this. So we'll say that's the fractional component, right? But there you have the fractional component. That fractional component is stored as a 32-bit integer. So how do we do that? Well, the way I think of this is I say, well, I have that many times 2 to the 32 divided by 2 to the 32, right? So to figure out how I would find just the fractional part of this, I'm going to multiply it by 2 to the 32. And then another way to do this is, can I do that? Oh, I can't do it because it's a float. So be it. I can probably do this and get the same value. So there's ways to use shifts in Python that are a bit odd, perhaps not obvious. That thing looks an awful lot like it should be rounded, and I guess it's easy enough to find out if it should be rounded because we're going to compare it against the baseline. So we have this integer value. This integer value represents the number over 2 to the 32nd that is the fractional component of square root of 2. And then we can simply convert that to hex and see that we have 6A09 E667, which is the same value on the left-hand side of the screen. We can do the same thing with the cube root, for example. So we can take 2 to the power of 1/3. And this is going to be a bit too large, right? Because we still have a 1 in there. So I think we take it like modulo 1 or something. And that is the 428. And it's kind of interesting to see where the 1 shows up in here, right? We're offset by exactly 1. Okay, so what's going on here? Well, essentially, we are splitting up numbers, and instead of having what we usually have, I think in like base 10 integer, right, where you have a ones place and a tens place and so on. What we're actually thinking about, or how I'm thinking about this, is we have a ones place and a 1 over 2 to the 32nds place, right? So my line of thinking is, well, we're smart people. Let's figure out how to do this in C. So, we'll leave these here because what else are we doing with them? Oh, I should put a some includes at the beginning of the file. Include standard.io.h and probably include standardint.h. Apparently, maybe standardint.h is not in C89. News to me. If that's a problem, we'll find a way to deal with it at some point in time. Okay, int main, and let's just begin with our minimal main. We'll return 0, and then we will see that we can get this to compile. I will come over here and I will type, well, first I'm going to verify I have primes gcc, primes.c, primes. Oh, I should do all of the big long thing that I'm supposed to do, which is, I have it somewhere here. Okay, gcc primes.c standard equals C89 wall wextra wearer pedantic slight optimization level. That's supposed to be an O, not a 0. And then we're going to specify the output as primes. Oh, I'm a silly goose. Primes. Okay, so nothing's going on yet. And what we'd like to do is we'd like to start computing these. So, how would I like to compute these, right? Well, there in fact is a C float type, and I'm not really about to use that. What I really need to do is figure out some way to treat integers like they're fractional parts, right? And so let's go ahead and figure out how to do that. Somehow we have to multiply two things together and get 2, but do we really have to get 2, or do we have to get something much larger than that? And so let's do that over here. So, oops, we'll run that again. I'm gonna basically make something that is a square root, but not quite. So what do I need? I need to get a 32-bit value back. Okay. And we'll call this square root fraction. I don't know, square root fraction. And it's going to accept a u int 32t. Guess we'll call that n. And what are we going to do with it? Well, we can't just divide this thing, right? That's not going to quite work. Can't really divide it by anything, right? We don't really have the notion of exponentiation in C. So we have to do something else. And the something else I think we should do is binary search. So that's the core insight I'm going to use. I'm going to use binary search. I'm going to take some value, I'm going to multiply it by itself, and I'm going to see how close it is to the target value, right? And the target value is going to be, let's see, the target value is going to be a 64-bit integer. It is going to contain the value of the 32-bit integer, but I'm going to cast it into 64-bit, and I'm going to shift it over by 32 bits. And this is going to be the target. So what I want to do is I want to find two numbers that when I multiply them together, I get that value. But one of the things that's going on here, right? And then let's see, what am I going to return? I'm going to return the uint32t cast of the target. This will implicitly be the fractional component if I'm working with 2 to the 32nds, because I will neatly cut off the integer components. So how is this going to work in theory? Well, we need to pick some value. We're going to multiply it by itself, and then we're going to have to sort of mess with it in some way to get it to be of the right size. So let's think of it this way. If I have 0.5 of something, and I square that value, I get 0.25. The value gets smaller. And if I have 5 of something and I multiply it by itself, I get 25 of it. The value gets bigger. When I'm dealing with these fractional things that I'm denoting as being in the bottom 32 bits of my 64-bit integer, when I multiply them together, they need to get smaller instead of bigger. Now, by default, they're going to get bigger. And so let's begin by just looking at some value and seeing what it turns into. So I am going to write a helper function that is going to square. And it's not going to be a real square. It's going to be some other kind of square that's going to square not a uint64t, right? But the notion of a fractional number stored in a uint64t. And so how's this going to work? I'm going to multiply n times n with the understanding that I'm multiplying things that are 2 to the 32nds, or fractional 1 over 2 to the 32nd, right? And so when I multiply two fractions together, if I multiply halves together, I get a number of fourths. If I multiply 2 to the 32nds together, I get 2 to the 64ths. So what I have to do is I have to then shift this thing back over by 64. The entire distance, or the entire size of the value, right? But I'm only going for a 32-bit value, so I don't have to worry about that too much. Now, the exact value I'm trying to get here is 0, because each one of these primes ends with a implied .0 fractional after it, right? So what I really need to do is I need to multiply two 32-bit numbers that are stored inside a 64-bit number together, and I need them to get to 0. And so I have to either increase or decrease n in order to get that 0. This is becoming quite a lot to think about. So let's do this perhaps a bit differently. We're going to break this up into an array. And we're going to do all of our multiplication internally in the array. The 0th index will be the integer component, and the 1th index will be the decimal component. We can bundle this back up into a 64-bit value or not, right? When we multiply two of these things together, we're going to have integer, and we're going to have fractional. We are going to take we are going to take the novel integer value, will be the integer value times the integer value. So we will create a uint32t return. Oh, I can't call it return. Retval size 2. Retval 0 will equal I times I. It will also equal plus 2 times f times I shifted over by 2 to the 32nd. Yes. So we'll take this value, which will be 2 to the 32nds, and we'll shift it over. And then ret val 1 will equal f times f plus 2 times f times I. And then we take the lower 32 bits. One little problem here. These are going to need to be 64 bits to be big enough to hold everything. Where the intermediate values are going to have to be 64 bits to hold everything. So we'll store everything in 32 bits, but we need our intermediate values to be inside 64. So uint 64t will have a 64-bit I, and then we'll have a uint 64t, which is a 64-bit fractional. There's no reason for these to be on different lines. I64 will equal I. We need input I's. Is that correct? Sort of want these to be... Oh, this is comically difficult to think about. So, somehow, we need one, two, three, four. We need int fraction times int times fraction. And this is, you're just going to FOIL this, right? It's going to be int squared plus 2 int fraction plus fraction squared. And then the thing is, the fraction squared is going to be shifted by 64, and the int fraction is going to be shifted by 32. And in order to do all of that, you have to store everything as 64 bits, right? Fraction times fraction is going to be shifted over by 64. The thing is, when I shift something over by 64, it's going to become 0, right? But perhaps that doesn't matter. Perhaps that's so small it will never affect anything. But perhaps it's not. Okay. Okay. So if I take values that are of size, that is a number of 1 over 2 to the 32nds, and I square them, all of the integer values are going to go off the end. I only really need the integer values, so these things are going to be too big. No, because it's stored in 32, so they'll be fine. I only really need those to be added to these values, the 2 times f times I. 2 times f times I is, so in the case of 1.414, right, we take 2 times 4.41, or 2 times 0.414, which gives us 828, and then we also take 0.414 times itself, which gives us 0.16 something, and so the 0.818, which is about 82, and the 0.16, which is about 0.16, adds up to 1. And so the 0.16 will be quite small, but not that small. And it will be, we need to target that this value, 2 times f times I, shifted to 32. Do we need to shift it? So 2 times 0.4 Regard those 0.4 as a high value, so it is a large number of 2 to the 30 seconds. It is roughly 2 to the 31, 2 to the 30 seconds. And we multiply it by 2, and it becomes very close to 1, 2 to the 30, or 2 to the 32nd, 2 to the 30 seconds. So that'll be a very large value times a very small value, resulting in a very large value. That should be fine. I don't think we shift this at all. The other one we shift a lot. If we take something that is very close to the 32nd by something that is very close to 2 to the 32nd, we multiply them together. Those numbers should get slightly smaller, which means we will multiply them into a 64-bit value, shift them, and put them back into a 32-bit value. So we need f64 to equal a uint64t of f. We need to take f times f, and we need to cast it. And before we cast it, we need to do a bit shift of size 32. And we can add these things right together, right? Oh, that's a 32-bit cast. That's a 64-bit value. And it is a 64-bit value that should be a 64-bit value. Okay, so we need we do need I to the 64 to equal uint 64t I. Oh, know that I need reval. Okay. We'll get R64. We'll initialize that to 0. Okay. So R64, we will add that, which is an integer number represented as something huge, right? Right, we have to shift this over by 32 because those integer values are representing not an integer, but a number of fractions of size 1 over 2 to the 32. So they need to be shifted over by 32. Which means when we multiply them together, they're going to be huge. In fact, they will necessarily be larger than the 64 bits. The integer values must be in the top order 32 bits, and when we multiply them together, they will go off the edge, which is fine. Never use them. Then we take, yes, the fractional values times the integer values, which are appropriately shifted. And so that is the equivalent of this f is the 0.414, which is a little less than 2 to the 31. This I is the 1, which is exactly 2 to the 32. So we have something that is about size 2 to the 32 times something that is about size 2 to the 31. That is going to appropriately fill my 64-bit chunk. And then I will shift that over by 32. I don't have to yet. I'm going to add retval to it first. Okay. R64. Ooh, I have, I pressed some key. I'm going to add f times f, which seems fine. I'm not going to do the shift yet. This can all be done on the same line. Times I plus f times f. These things are all of approximately the same size. Then I'm going to return the uint64, no, the uint32t of R64. Okay. Shifted over by 32 bits. And so that will give me a value that is going to be the fractional component of the square value or something, right? And so the way we're going to test this is we are going to square some value. What are we going to square? It's the wrong type. For now, we are going to square 2. No, we're not. We're going to square 1 and 0.5, which is 1 shifted over by 31. And that is going to give us back probably 0.25, which I think is going to be 1 shifted over by 32. So we're going to print out what am I going to print out? I'm going to print out the fractional value, which is we're going to do it in hex so we can see it in a new line. It's going to be the value n, and it's going to be a 32-bit value. Okay. Square root fractional. Doesn't matter what I put in there for now. Okay, we'll put in 2. Okay. Let's run that. Let's clear. Expected expression before. So what have I done wrong here? This is not a cast. This is being treated as a function. That needs to be a cast. Unused variable f64, right? These all should be 64s. 64, 64, 64, 64. It actually would have been easier to rename something else. That's completely reasonable. Okay, let's save that. Clear. Target undeclared. We'll just return n. Or no, I call it primes. That is, watch this. Okay, so we take that value, which is a 4 times 1,000 times 10,000 or something. Right, so we take x and we divide that by 2 to 32. And it's 1% or something. Maybe that makes sense, right? Much is this? Oh, I need to see it in hex. So I took this much and probably that much, and I multiplied them together. And so that's the same thing as 3 shifted over by 32, probably. Wrong shift direction. That in hex. No. Hex 1, 31 plus 1, 32. There's some sort of associativity going on here. I'm trying to figure out what these numbers should be. Okay, so that should be 1, 8. I was off by 1, so it's probably 3 to 31. Okay. 3 to 31. Square root of that is that much. Well, what's the square root of 1.5? It's possible all of these numbers are close to being correct. Aren't I just squaring it right now? Oh yeah, I'm only squaring, right? So 1.5 squared is 2.25. That's a quarter. This is a quarter because it is 1, 2, 3, 1, 2, 3, 4 divided by, right, yes, it's this thing. 2 to the 30, yeah. It is, it is 1 quarter. So my square calculation is correct. And with the square calculation correct, I think we can get on to the next thing, which is guessing and checking. So let's go ahead and see how we can sort of guess and check this thing. Let's see. I need to, let's see. I need to increase or decrease this. Well, first I need to pick a candidate value, and then I need to increase or decrease it to get closer to something. So what is the target there? This kicked back 1 quarter. .5 times 1.5 returned 0.25. So it's giving me only the fractional component, right? That thing is currently larger than 0, and we want it to be smaller than 0. And I think what we want to do, see, the thing is we can see if it's larger or smaller than 1 by passing back a 64-bit value. Like, there's a lot of appeal to that, right? So, like, if I do this, and I come in here and assuming that's like a long x or something, I'm probably going to get something a lot closer to 2.25. Unsigned long int. Well, I'm going to leave this cast here so I don't have to rewrite it if I change my mind later. I am going to try and now return 64-bit values. Signed long, that is not a 32-bit value. Oh wait, n is. Oh no, I did the thing I always do, whatever that is. There's probably 16 of those. Okay, so we'll make a new value. Uint 64t square. Print the square. Right. File. We'll run. And we are still only getting the 0.5 because I'm not multiplying the integer components at all. And so, no, I should have still gotten it, right? Because the 0.5 times 0.5 is 1.25, even if it's not 2.25. 2 times. So this should be 0.5. This should be 1. This thing should add up to 1. 2 times f16, or f64 times I64. What is it, 16? Oh, it's 16 nibbles? Okay. It's possible LX is too small. Am I just clipping it? So I think I'm not totally sure that I'm printing all 64 bits. ISO. Oh, C9. Oh, we're gonna turn off C99 or C89, and that'll maybe help us a little bit. Just for now. That help us? No. That's still giving us exactly that much. Okay. So what is the thing that I want to do? I want to oh, right, because I times I that will be overflowing. This will overflow and won't go anywhere. So I won't ever see the integer components at all. It doesn't matter that I'm returning a 32 or 64-bit value. So we're going to drop in the 32s. Change this back, 32. 32. Okay. This is currently too large. And so what we want to do is we want to determine whether it's too large or not. And the way to determine if it is too large is we have to pass back a true or false value rather than what the square is. So we want to know if this thing is overflowing. How do we determine if it is overflowing? We don't multiply this by 2. We add it to that, and we see if it is bigger or smaller when we add that in. So we see we don't want to actually calculate the square. We want to calculate if the square is too large. Where we're going to do that is we're going to calculate this value. We're also going to have a test value. The test value is going to equal the potential return value plus f64 times I64. Is that all we have to do? Can this thing already be too big? No. the absolute largest integer value times the absolute largest decimal value must not be larger than the absolute largest integer value, right? So all we have to do is see if R64, we can even divide this. I'm in insert mode. We just see if that value is bigger. We see if it's bigger than 1 shifted over by 63, I think. So 1 shifted over by 63 is half. Yeah, okay. So return R64 greater than 1 did 63. And that's probably going to turn into an integer. Okay. Might log something here later. So, that is true if the square is larger than 0, otherwise it is smaller. Just have the int here. Just print it like so. Okay. Square. Not in insert mode. Ooh. Square larger. Not supposed to be an I there. Left shift count greater than width of type. Really? Oh, because it doesn't default to goodness me. Okay, I'm not in insert mode. Now I'm in insert mode. I didn't want to be in insert mode yet. Okay. I was still not in insert mode. Int 64t I sure. That should be larger. Let's see what it is. Print f sent lx new R64. Okay. I don't even think I'm close to being able to understand this in an hour. It's the printf percent lx new line R64. Should be something big. Okay. How large is that? Or let's see. So that is a 6, and to be bigger than that, it would need to be an 8. I want to calculate what f64 times I64 is, because I think that is 0.5 times 1. f64 times I64. Oh, I should put in a new line. I can see them lined up against each other. I, and right, primes k. Yeah, I definitely added something to that, and then it got smaller, right? That has to be what happened. Because 6 is smaller than 8. There's an addition. Did it overflow? So I should have 0.5 times 1. It should be 0.5. Then I should have 0.5 times 0.5. And then, yeah, I'm taking half of that because I was going to double this. But yeah, that 0.5 times 1 that's huge. See what, I have no idea where my cursor is. Okay. F4 times F64. I will insert another. Oh, I should be yanking for that. Okay. So that 4 is going to become a 2. That 2 is going to be added to 8, which would make an A. A is one higher order bit. I should at least print what 1 shifted over by 63 is. U int 64t 1 by 6. I'm not on one line anymore, so how do I fix that? Do a new line here, new line here, and here. Should be a new. Oh, I don't have A style, do I? Okay. Okay. So I am adding something. Well, I think I just have to say that it's considerably harder than I thought. That's not true. I thought it was going to be exactly this hard. It's very easy in Python. It's very hard in C. I was going to write a binary searcher over a fixed precision fractional binary number. I was going to use that to compute all the various prime values and it's very hard because you keep overflowing in both directions, pretty much no matter what shifts you do. So the lesson here is that numbers are hard. And let's just go back to doing it in Python to see how easy this is with modern languages. Okay, so we take 2 square root. Okay. You could even do something like say, hey, that's too small. We're going to increase it by a little bit. That's too big. We're going to decrease it by a little bit. Now we're going to decrease it by a little bit. We're going to increase it by a little bit. How much should I increase it by? Let's see, I just increased it by 0.25, so I'll put a 6 here. That's too much, so I'll decrease it by 2. No, that's still a little bit too much, so we're going to drop this 5 to a 2. Okay, we're going to bump the 5 to a 3. That was too much, so we'll do 2, 5. This is relatively easy in decimal notation, right? This is what I wanted to do. And a little bit too hard in C for me. Ooh, how close am I? Nope. And this is sort of just the application of binary search. It's fun, but you can write a script that does this. Presumably there's some way other than scripting to do it, but I couldn't figure it out. If you would like to calculate the primes yourself, I will give you some large amount of extra credit. I'm curious to see how you would solve this problem. It is completely trivial in Python. It is not that hard in C if you use libraries. The library is, I think, GMP, which stands for GNU Mixed Precision. And if you don't do both of those things, you'll have a pretty bad time, is my impression. All right, thank you. This has been my effort to calculate the fractional roots of prime numbers, and I successfully calculated the square of a fixed precision non-integer value, which is more than nothing, but not very much. Stopped jobs.